Linear partial differential equations. Analysis and numeric assignment help. For any assignment-related queries, call us at +1 678 648 4277. You can mail us at support@mathhomeworksolver.com or reach us at https://www.mathhomeworksolver.com. Problem 1. Distributions. This problem concerns distributions as defined in the notes. Continuous linear functionals f a phi from test functions phi d, where d is the set of infinitely differentiable functions with compact support, i.e. phi equals 0 outside some region with finite diameter, differing for different phi, i.e. outside some finite interval, a, b, in 1D. In this part, you will consider the function and its weak derivative, which is connected to something called the Cauchy principal value. mathhomeworksolver.com. I show that f(x) defines a regular distribution by showing that f(x) is locally integrable for all intervals a, b. 2. Consider the 18.01 derivative of f(x), which gives suppose we just set f(0) equals 0 at the origin to define show that this g, x, is not locally integrable, and hence does not define a distribution. But the weak derivative f of phi must exist, so this means that we have to do something different from the 18.01 derivative, and moreover f a phi is not a regular distribution. What is it? 3. Write where since this limit exists and equals f of phi for all phi from your proof in the previous part. Compute the distributional derivative and show that f a phi is precisely the Cauchy principal value. Google the definition, e.g. on Wikipedia, of the integral of g, x, phi, x. mathhomeworksolver.com. 4. Alternatively, show that, which is a well-defined integral for all phi d. B. In class, we only looked explicitly at 1D distributions, but a distribution in D dimensions Rd can obviously be defined similarly, as maps f a phi from smooth localized functions phi, x, to numbers. Analogous to class, define the distributional gradient f by f, phi equals f minus phi. Consider some finite volume V with a surface del V, and assume del V is differentiable so that at each point it has an outward-pointing unit normal vector n, as shown in Figure 1. Define a surface delta function delta, del V, phi equals phi x dd minus 1x to give the surface integral of the test function. Suppose we have a regular distribution f, phi, defined by the function where we may have a discontinuity f2 minus f1 equals 0 at del V. I show that the distributional gradient of f is where the second term is a regular distribution given by the ordinary 18.02 gradient of f1 and f2, assumed to be differentiable, while the first term is the singular distribution. mathhomeworksolver.com. You can use the integral identity that to help you integrate by parts. 2. Defining 2f phi equals f 2 phi, derive a similar expression to the above for 2f. Note that you should have one term from the discontinuity f1 minus f2, and another term from the discontinuity f1 minus f2. Recall how we integrated 2 by parts in class some time ago. Problem 2. Green's functions. Consider Green's functions of the self-adjoint indefinite operator a equals minus 2 minus omega 2, kappa 0, over all space, omega equals R3 in 3D, with solutions that 0 at infinity. This is the multidimensional version of problem 2 from set 5. As in class, thanks to the translational and rotational invariance of this problem, we can find g, x equals g, x minus x, for some g, r, in spherical coordinates. A. Solve for g, r, in 3D, similar to the procedure in class. I. Similar to the case of a equals minus 2 in class, first solve for g, r, for r greater than 0, and write g, r, equals limp 0 plus ff, r, where ff, r, equals 0 for r less than or equal to e, hint, although Wikipedia writes the spherical 2G, R, as 1/R2, Rg, it may be more convenient to write it equivalently as 2G equals 1/2, Rg, as in class, and to solve for H, R, equals Rg, R, first. Hint, if you get sines and cosines from this differential equation, it will probably be easier to use complex exponentials, e.g. air, instead. MathHomeworkSolver.com 2. In the previous part, you should find two solutions, both of which go to 0 at infinity. To choose between them, remember that this operator arose from AE minus it time dependence. Plug in this time dependence and impose an outgoing wave boundary condition, also called a Sommerfeld or radiation boundary condition. Require that waves be traveling outward far away, not inward. 3. Then, evaluate AG equals AG, Q equals G equals Q, 0, for an arbitrary, smooth, delta, x, in the distributional sense, AQ, localized, test function Q, x, to solve for the unknown constants in G, R. Hint, when evaluating G, AQ, you may need to integrate by parts on the radial derivative term of 2Q, don't forget the boundary terms. B. Check that the omega 0 plus limit gives the answer from class. MathHomeworkSolver.com Problem 1, A. Solutions, f(x) is bounded in every interval except intervals containing x equals 0, so local integrability is trivial except for intervals containing x equals 0. It is sufficient to consider integrals because any interval, a, b, containing 0 can be broken up into and f minus x equals f x, so we only need to show that the latter is finite. But we can now just do the integral explicitly. Since, as can easily be seen e.g. by L'Hopital's rule applied to 2g x is not locally integrable for intervals containing the origin. For example, therefore, f phi equals f minus phi is a singular distribution. MathHomeworkSolver.com 3. We write f phi equals lim 0 plus fl phi and integrate by parts in fl phi equals fl minus phi. In the last line, the first limit is precisely the Cauchy principal value of g, x, phi, x, dx, CPV equals remove a ball of radius e around the singularity, do the integral, and then take the e0 plus limit. The second term vanishes because, since phi, x, is continuous and infinitely differentiable, phi, e, minus e, vanishes at least as fast as e0, so its product with ln e vanishes in the limit as in part, I. 4. Use f phi equals f minus phi equals f minus phi 0 equals f phi minus phi 0. Then substitute phi minus phi 0 into the previous part, and note that since the integrand is now finite as x0, since phi x minus phi 0 goes to 0 as x0, at least proportionally to x or faster as in the previous part, we can now just take the limit to write without using the CPV. B. Solutions. I. Let VC denote the complement of V, the exterior region outside V, i.e. VC equals RD\V, and note that del VC equals del V, but with the outward normal vector reversed in sign. We write MathHomeworkSolver.com as desired. 2. In this case, we will need to integrate by parts twice, but we can just quote the results from the notes on elliptic operators from class, where we integrated by parts twice with minus v2 already, albeit keeping the boundary terms from del v that were 0 in the notes. But the first term is delta, del v, f1, x, minus f2, x, nv phi, sadface nv, delta, del v, f2, x, minus f1, x, phi. By the definition, note the sign change of the distributional derivative nv. Note that this is a scalar derivative in the n direction, not a gradient vector. The second term is a surface delta function weighted by nvf1 minus nvf2, the discontinuity in the normal derivative. And the last terms are just a regular distribution. So, we have